I would like to introduce Lior Horesh to you. He's in the quantum computing group at IBM Watson Research. I think we are looking forward to an amazing talk because he has some surprises for us and also a very high aiming title, so towards the Nobel Prize machine. I'm looking forward to your model discovery.
Thank you very much. So thank you very much for the invitation. I'm very delighted to be here. Actually, indeed, the original title was the Nobel Prize machine, so I tuned it down to be modest with you guys. Probably it started actually with my midlife crisis. I figured that probably I will never be able to get a Nobel Prize. Sometimes you know, reality bites you, and after several attempts, you realize that some of you may, but probably I will not. But then I said to myself, you know what? Maybe if I cannot get a Nobel Prize machine, or if I cannot get a Nobel Prize, I can build a machine that will get one for me, right? So I will describe you our attempts to do something like that. It's a bit pompous, I know, and there is a surprise as well later on. So I hope that you will enjoy it. Sit back, relax, and enjoy the ride. So really, on a high level, that will be a summary of what we are trying to do. There is some underlying phenomena that we may observe. What we want to do is to come up with that wonder machine that will ingest that data and spit out a Nobel-worthy equation, and of course the outcome is so I guess we are all on the same page now. So I will start with acknowledgement. So actually these folks did probably a lot or even majority of the work of this interesting exotic project. And now I will provide a little bit of an introduction. We go a step backwards. So we know that many of today's challenges can no longer be supported by a single scientist, right? So this is Atlas lifting the world in his hand. So nowadays we know that we have to collaborate in one form or another. Back in the 70s, the notions of IQ was very, very popular, the individual IQ. And now people are talking more and more about collective intelligence, not the intelligence of a single individual, but multiple people. And if you look at the definition in Wikipedia, actually it even extends beyond that. And taking another step, we know that collaboration and open research and things of that nature, such as Wikipedia, Linux, CAPTCHA, Foldit, all of those things facilitate innovation which is greater than any individual's effort, right? And the Sloan Center for Collective Intelligence in MIT extend that definition beyond the collaboration between people, but also collaboration between human and machine, and this is really the rationale in this specific line of work. So going again a little bit backwards in time, with this funny graph of repeatability and man and machine, in the past we gradually figure out that there are some actions that are repeatable and we can automate them in one way or another. So starting with maybe seeding, and then we figure out that we can harness some poor animals to do the job for us. Later on, with the Industrial Revolution, we managed to automate more sophisticated sets of actions. And the first revolution, the second Industrial Revolution, some claim that we are now in the fourth or the fifth one. Looking into the invention of the computers, that further revolutionized and allowed us to automate more complicated tasks. And now we are in the realm of self-driving cars and AI. So we are trying to gradually provide more and more innovation that a machine can perform for us. But there's a question is for how far we can really push it, and whether machines one day will completely makes our ability to think obsolete. So looking into the cognitive function pyramid, and you can argue whether all of these entries should be listed in that way, and whether the order of them should be ordered in that fashion. But there are different faculties of our brain that attend to different cognitive tasks, and some or most people would agree that creativity and discovery should be somewhere at the top, right? These are things that, as of now, AI is definitely struggling to perform. We can do learning, we can do inference, we can do perception, we can do decision making under uncertainty, some of interactions, but creativity is something which is quite challenging. The problem with creativity is it's a little bit open-ended, so it's more difficult to qualify whether one creative work of art is any better than another one. Discovery or scientific discovery is something that has actually more ability to validate and verify, and this is why many actually put that at the very top of that pyramid. So, looking more specifically towards the aim of what we were doing, so we were trying to essentially figure out how to model, to design mathematical models, and we know that mathematical models are linking between, trying to find a consistent link between some input and output of a phenomenon or a process. The discovery of model involves some decisions that we need to make mainly between the complexity of the model and how realistic it is in its predictions. Although there are many other different trade-offs that one can consider in terms of accuracy, robustness, functional complexity, computational complexity, interpretability, and so forth. There are many other virtues that one may want to require from the model, and it's up to you to decide how to facilitate those and which one of them is more important for you. Now, traditionally, we have two main schools of mathematical modeling approaches, and between them actually there used to be a very big gap. That talk yesterday was actually a very nice way to connect between some of the more first principles, PDEs type approach, and the data-driven. But one school is really the first principles, schools that try to derive things from fundamental relations, and the other one is taking the other extreme of being completely agnostic with statistical models and data-driven approaches. And on the first principle side, obviously we can see that there were many giants of science that came before us. The beauty of their work is that they came up with pretty universal relations, right? So Maxwell equations, for instance, they undergo Lorentz transformations, so they can be valid also in other speeds or in anywhere in space, right? So it's not that this law is only valid here in this room at this time. Those universal links are they would also hold on the moon or any other place, right? On the other hand, if you look at the difference between the dates, these are when they were born and died, but in principle, it took quite a while to come with such discoveries and a lot of talent, of course. We should not underappreciate that. Now, I mentioned some of the giants, and few people actually asked me, okay, there are no women in your slide, and I said, actually, that's a fair comment. And our real role model is actually Marie Curie, because she's the first scientist to actually get more than a single Nobel Prize. She got 2 of them. So, and this is exactly our purpose, right? So she's definitely our inspiration. So now, looking at the other side of the map, we look into data-driven approaches. Again, they try to provide a link between input and output of some phenomena, but there is one disclaimer that we often sort of disregard, which is we have a generic functional form, which we bring in before we even see the data. And that functional form, it's not that those that are doing that are so silly about that disclaimer, but we pick those functional forms because they are computationally exploitable. We know how to solve these functional form very, very quickly or large problems, and therefore it is actually somewhat sensible. They can be effective, those approaches, of course, when we have little knowledge about the domain or the process that we are trying to model, and in particular when we have big data. Because we need essentially since the functional form is predetermined and it may have very little association with the underlying process, we need a lot of data to essentially tweak a generic model to do what we want it to do. So they may fail to generalize the underlying behavior, and to be honest, again, we brought that model before we ever saw the problem, so don't expect any much of interpretability from such a model. So in this slide, I try to give a little bit of intuition as for what in my view at least limits conventional machine learning. So we have here 2 functions. One is a true, let's say that the solid line is the true function and the dashed line is our mathematical model. And we're now going to bring some data. So I use this staple to condition my my model to the true function. So let's imagine that these are measurements of different points, and we can keep on doing that. Probably need to put more staples in, okay? And we get some approximation of our function, right? Now, one thing that is important to notice is that while, let's call the original function f and the model g, while f at xi may be equal or very close to g at xi, for all those xi's in the training set, this similarity between the functions themselves, f and g, in functional spaces can be arbitrarily far, right? So the fact that we have no similarity between them means that when we are looking into things like the trail of this one, interpolation we can do very well, but extrapolation would be something that can be very challenging for such methods. So one resolution that people try to bring is saying, oh, let's bring more data in. Hopefully that will solve the problem, right? So you can bring more data, and this time I brought a much more efficient stapler, and indeed it can get that part very, very accurate, right? But we still haven't done much about the out-of-set instances, right? So generalization is really almost by definition challenged by that dispersity between the original function and the specific choice of functional form that we chosen for the model. So here in this table, we were trying to summarize the advantages and disadvantages of the two approaches, and deliberately we put them in contrasting colors to show that it's not that one approach is any better than another, but really they're actually quite complementary in some regard. So if you look at the first principle versus data-driven, with respect to data reliance, obviously you don't, or you need a lot of data for data-driven. Oftentimes you need very small data for first principle approaches. On the other hand, you need a lot of domain expertise, which you don't need for data-driven approaches. In terms of robustness and fidelity, we mentioned that first principle models tend to have better universality, and they hold on a broader set of conditions, whereas data-driven approaches are very specific to the training instance that we provided, right? Another thing is adaptability. Obviously, it's very easy to deploy a data-driven approach to a new problem. We cannot say the same about first principles. And lastly, interpretability, which is actually a very big thing in some disciplines. First principles is definitely winning here, but it sort of makes sense, right? If you start with something which is agnostic to the nature of the problem, you don't expect it to be interpretable. So that brings us to a fundamental question, which is, should you derive or essentially let the data drive, right? And in some regards, we say that the two approaches should not be regarded as fundamentally different. The main difference is indeed the functional form and the automation. And indeed, it makes sense to try to combine these two approaches to get models that are generalizing better, have some interpretability, and hopefully can learn from smaller data. So how do we go about it? So how do we overcome this fundamental issue of data-driven approaches? So the solution is actually discard that assumption that the functional form is a fix before you ever did something. Because with that assumption, you cannot really go too far. So try to come up with a free-form model discovery approach where you try to figure both the functional form and the parameterization all together. And the one advantage is that actually, if you look at neural networks that are very popular these days, typically there you work with a very limited set of primitives even. So the operators are activation functions, the sigmoids, the hyperbolic tangent, and so forth. You can actually pick whatever you want. So if you look into some funny graph that describe a phenomena, you may say that looks like a sign that is multiplied or embedded within, or composed within an exponent, right? This is something that you will not be, or will not easily be able to perform with other approaches. Now, that proposition sounds intriguing and interesting, but obviously there is a big flaw here, because there are infinite number of models that can map from a set of point to a set of point, right? So obviously you don't want just to find a model. You would like to choose a model that will have some requirement upon its complexity. I would like to find the simplest, in some measure, a model that will actually do that mapping between those points and will also honor essentially their values. So we do a proper mapping between the two. And the other thing that we can do is actually, and I will get to that a little bit later, you may want to also incorporate other virtues or invariances associated with your understanding of the phenomena, even if these are very implicit level understandings. So the way we do that, we articulate this problem as an optimization problem, and hopefully that's something that we all appreciate here and grew to love. We define a grammar in which every meaningful expression is a sentence in the formal language that we define. So every sentence is actually a mathematical expression. You can think about x plus 4 is not a valid sentence in my language. It's not a valid equation. So I can actually articulate what is my grammar of writing an equation, and in principle I can express every mathematical expression in an expression tree, and this is what we did. And what we have in that formal language, we have three different types of entities. We have operators, marked in green here, so plus, exponent, sign, what have you. Variables such as this x, y, z, and of course constants, right? So you sometimes need those half or 3 or whatever, pi. And here you can see this expression 3 result in the mathematical formula that you see here on the right. And so we encode that grammar as a set of constraints, and essentially we look in that space of sentences for the ones that on the one hand honors the data when we evaluate them at the training point, while finding the simplest one among all of which. So that's really the proposition. Now, how do we go about it? Because if you think about it, we have two very different types of optimization requirements. On the one hand, we have discrete choices. The functional form itself, think about that tree. The structure of the tree is discrete. You either branch here or not. You either have a sign or an exponent or an x or a half at a given point, and that's a discrete decision, right? On the other hand, the entire function is a nonlinear function. So I need to be able to optimize both on discrete variables and on continuous variables altogether. So, I probably already explained, but the mixed integer or the integer part is really attending to those integer problems. And this is Ralph Gomory. He used to be the head of our research division in IBM Research. He was one of the pioneers with Gomory cuts to come up with integer programming approaches. Back then, the original motivation was he was working for the Navy. The Navy asked him how many carriers we need to produce. The answer was 1.3, which is somewhat a challenging proposition for building something. And then he came up with a whole nice theory of how you actually solve problems where you have integrability constraints or requirements, right? And then for the nonlinear programming, there's another anecdotal story of George Danzig when he presented his linear programming theorem at the Econometric Society of Wisconsin, and there are a few high-profile fellows there, Hotling, Kopman, and von Neumann. And after his lecture, Hotling was essentially shouting, more or less, but we all know that the world is nonlinear, right? So I put another Siam paper to emphasize that. So we know that we cannot model everything just with integers. We cannot attend to everything just with continuous variables. I know that in our community we tend to lean more towards the continuous side, but there's a whole world of integer programming that we should respect and learn something from. So how do we mathematically cast this problem? So we can write the following optimization problem. We are trying to minimize some measure of complexity, C. S is my sentence or my expression, such that the discrepancy, D, between evaluation of my sentence, my mathematical expression, at the point X is close to the data, the true data that I measured, D, with some bound. So tau is some error bound that I can provide. We require that my sentence S is a valid mathematical expression, so it is parsed. And then we have some requirements that S is indeed part of my language or my alphabet, if you want. We may introduce some other nonlinear numerical bounds. And if you want, we can actually incorporate also some invariances. We may believe that there is some symmetry, so we can actually incorporate that symmetry as part of our requirement for the sentence. Or if there is some conservation law or anything that is invariant, we can actually try to impose that either explicitly or implicitly as a constraint. So in terms of how do we go about solving those problems, and they are indeed very, very complicated problems. We are challenged with just doing NLPs properly, and we are challenged with doing integer programming properly. Combining the two together is even a more complicated proposition, and there are different approaches, mainly based on different forms of decompositions, enumerations, relaxations, and sequences of which. There's one particular approach that we've chosen to work with, which is essentially the spatial branch and bound or branch and reduce. That I will provide you a little bit of intuition how it works, and hopefully you'll find it interesting. So imagine that we have a non-convex function, and you know that non-convexity is something that can be problematic. So first stage, we're just going to split that function to two regions. Second, we try to find an underestimator for each of those regions, and then we can solve some relaxation and get a lower bound. Now, we do require that the lower bound is actually convex, so it provides us a globally optimal lower bound. And for the upper bound, we can be a little bit more loose. So, for instance, here on the left, we have this lower bound, with this upper bound, and here on the right, we have another one for the other section. And one thing that we can see from this image is that since my upper bound on the right is lower than my lower bound on the left, what is a reasonable conclusion here? Essentially, there's no point for me to further explore anything on the left side, right? So essentially, I'm gonna throw away that section, and I will keep on repeating that process on the right. This is really on the high level. So with that approach, you can actually try to, first of all, rediscover some known relations. So we started, that was the first formulation of that work. It was probably 2.5 years ago, rediscovering Newton law of gravitation. We are here, Newton Institute, so we have to give him the credit. Then the same thing for Einstein's mass relativity relations. And after we did that, one thing that bothered us was we were getting constants, but those constants were somewhat like numbers. And oftentimes you may ask yourself, maybe I can do something more clever about those constants rather than just putting them as they are. So back in 1979, Gauss really computationally, he observed that relation. So this is actually a recursive relation that defines the arithmetic geometric mean. Is the left part and the right part are consistent up to the 11th decimal point. Now remember, back then he didn't have too much computational power. It was only really his head, and he used to maintain a diary with all of the constants that he found. So I actually have this one on my desk. So that's my cell phone camera. So you do have those things, or they used to be even useful several years ago, where you wanted to have a lookup table where you found, okay, I have this constant. What is an interesting decomposition of that constant into pi, h bar, whatever? Some of those parameters that you may think that they are useful. So what we did was using exactly the same machinery, now introducing a set of primitives rather than just operators. We have our primitives would be pi, Euler number, the magic number, for instance, G for gravity, and so forth, and then you can provide a set of or a superset of operators that you may want to link those things together, and you then can try to find an interesting or hypothesize a decomposition of a number to those constants. So now, actually I have two options. Maybe, okay, probably going to take time to run it. Let me launch something in the background, because it will take a few minutes, and if it will take too long, we can just, I have a video of that, so we can always fast forward that. So here is an example of something that I'll explain in a second. I will just going to run it in the background, going to launch it now. Oh, complains about some things? Okay, I'll just go with the video then. Maybe it will be easier. I'm not in the right folder probably. Indeed. 1 second. Oh, yeah, now it runs, sorry. Okay. So it will run in the background. I'm not sure if you can see much, so maybe I'll describe what's happening. So the first experiment is related to the Galileo pendulum. And so back in 1589, he was learning some medicine, sitting in his room, and the wind blew, and he noticed that the chandelier was moving. And then he went to the Pisa, to the great chandelier in Pisa, which is in this image, this picture, and he was, back then there were no atomic watches, no GPS even, so he had to use his own pulse to measure time, and he was trying to figure out how the consistency of the period with that chandelier. And one thing that truly surprised him was that independent of the exclusion size, whether it was very small or very large, it took exactly the same period time. So it was independent of the amplitude in small angles, if you want to be of that pendulum. So he derived some relation that we will see in a second, but that was actually the beginning of he invented essentially the pendulum watch, and which replaced the sand watch and the water watch. So what I will do now is I will reveal this funny object. So I brought this all the way from New York, and the TSA folks didn't like it that much, but it's here. So can you all see that? Okay, let me hope that time. So this is called a wave pendulum, and this is what we were using to do the experiment. So I will now going to launch this thing. Oh, not good because it's slid. Okay, let me restart on a more solid ground. Probably I need a volunteer from the audience to help with this. No, not good either. Wait. Okay, it got entangled here. Yeah, I need somebody to stabilize. Just if you're the right man. Yeah. Actually, this one to stabilize. Can you hold this? Yeah, because that's a problem. Luckily, you can see that I'm not a real experimentalist. No, my goodness. It worked very nicely yesterday, so I think probably it was. So that was the main problem with. 1 second. I will do it one last time, okay? And I do apologize. Is it entangled? Ah, I see. You know what? You cheat. Nobody saw. I just pulled it a little bit closer to its friends. And ready? Okay. So we will let go, and I know that probably you're going to ignore everything I'm going to say from now on, and you will all be watching this thing. So for those who maybe just watch this funny thing online, so what we did was to figure out the relation, we wanted to have one variation. We wanted to change different parameters in this aperture and see how it behaves, right? If I would just have one link length, maybe I will not discover some relation associated with the link length. So we need more than a single pendulum to do that. And the other thing is so we we have actually a nice setup where we take a mobile phone and we just take video of that, get the coordinates, and directly do the recovery of the equation. But the nice thing about it is that with the raw data, we can feed that raw data into the Nobel Prize machine. Let me go. So let me show you. So this is raw data, for instance, that we collected without any transformation, putting it in the proper coordinate system, nothing. Take that raw data, you launch the code, and so we use, to solve the mixed integer nonlinear programming, we use Baron, which is a package for mixed integer nonlinear programming. Within that, we use Cplex and IP-opt for the nonlinear, effectively. And that thing can take some time, right? So I'll probably going to spare you some of the, and then we can see whether the other one finished by now. But let me see. Let's go here. So it can take some time, and that was actually an older version that was from last year. We have ever since we improved some stuff. Initially, it looks for a lower bound. The upper bound is not set yet. At the beginning, it doesn't find something, and then gradually it finds different feasible solutions. And maybe we can skip. I know that I have time, but probably not that much. So I'm going to skip. And at the end, are we close to the end? It spits out the formula. So you see that square root of L. So what we did, because we had a challenge, we couldn't figure out that square root. Anybody knows the equation here? I hope everybody. Yeah. So now it's written. So that pi over square root of g is very close to 1. It's like 1.002. And we really wanted to get that equation, right? Like that constant as well, not only the square root of L, which is impressive by itself, but so what we did was, rather than measuring a single crossing, we measured the difference between the ith and the jth crossing. So we gathered enough statistics to be able to do that, despite the fact that we were measuring things in a somewhat unprofessional way. But it spits out the right equation. And the nice thing about the framework, it actually provides you globally optimal certification. So what we found, I can guarantee you that you will not be able to find a simpler equation that within the bounds of error that we allowed the discrepancy of the evaluations of the function to be, you will not find a simpler one that does it. And that's actually a strong statement. So that's the respective tree of that expression. And now often there is a big question of, okay, we're all doing neural networks these days. How does it compare to neural network? And maybe it's an unfair question, because there are things that neural networks can do that this thing I don't imagine it doing in the future. So obviously I was very biased in this table where you see the green and the red. I took only the features that I like, but still, I think it's remarkable. So if you think about the neural network, one, and that showed it very nicely, one way to see it is this funky graph of different neurons and their connectivity or topology. But really, you can always write it down as an equation. And this specific one looks like this equation. Obviously, if it's deeper, it just becomes longer and longer. But the whole idea is you have some affine transformation, activation function applied upon that. Then you put it with some weights, add another bias, and keep on going backwards, right? It's a very simple proposition versus that equation, right? So I guess that in terms of simplicity, most of you would vote for the one on the right versus the one on the left. So on the left, we have something which has a fixed topology, a fixed structure. On the right, we have something which is free form. Typically, we have a limited set of primitives that we use for neural networks for a good reason. We can exploit that, right? If we know what we put in, we know how to go about it. Here, it can be anything you want. And I'll speak about it even beyond, right? So it doesn't have to be even necessarily something like a square root. It can be arbitrarily, an SVM, right? Or a DNN can be an object here. Now, other things, so interpretability, I guess, obviously the this one is more interpretable. You can see how the length and is related to the time, and it's very, very clear to read this. We actually did that thing with only 3 pendulums out of the 15 or the 10 that we had in the measurement. So, and within that, we can actually manage to get it down to 18 measurements, so 6 from each one of them. 3 pendulums, 6 data points, and that was enough to get that fundamental equation. So it can definitely learn from very, very small data. The other thing is universality, and obviously Kolmogorov came up with a proof back in the 50s that neural networks are universal. There's no nonlinear function that you cannot represent. We can say the same, but because actually we can represent a neural network with that very generic structure. But I would say that we can actually do more interesting stuff. And if you take universality as not in that context, but in the context of being able to come up with a relation that would be valid here and would be valid on the moon, probably we have an edge here. And the other thing is as I mentioned, is we can certify global optimality of the solution that we find. So originally we had, that's another experiment. So Neil deGrasse Tyson was expected to come to visit us and to feature that in his show about astronomy. It will happen in the next quarter, but in preparation for that, we took some data set from NASA of exoplanets. And what we have there is the orbital period, the mass of the host star or the star, the masses of the revolving planets, and the major semi-axis, right, which is essentially, because it's not an ellipse, it's not a circle really, right, as we know. And we actually feed up there are many other funny features, so we fed them all as well. Not all, but we fed some of them as well, because we don't want to assume that we know what is the answer in advance. We would like to find the simplest expression, and because we are looking for the simplest expression, sensitivity analysis is something that happens here for free, right? So in this specific one, we took 3 different, so it's not solar system, but systems, star systems. So the first one was our own solar system, another one called Therapist, and so forth. And one thing that we wanted to see here is what happened as we relieve gradually the requirement or the upper bound for the error. So so what happens is actually something very interesting. So if you're familiar with the equation, essentially what it says is that t squared, the period square, is equal to 4 pi d to the third, and then divided by g multiplied by the mass of the hosting star, or the sum of the 2 masses actually. That's the more complete equation. So we got that relation without the little mass, because the difference between the small mass and the big mass, they were on very, very different scales, and the errors that we had in that data set did not allow us to discover the small mass relation. But as you allow upper bound of error of up to 2%, you actually get the right equation. As you loosen it up, what the algorithm would try to do is actually say the simplest, you ask me for the simplest one that is still valid within that error bound, so it will start getting simpler and simpler expressions that would still adhere to that tolerance. So this is just to exemplify what really happens in practice. Now, it's very nice to discover things that people have discovered before. That's probably not going to take us on the fastest track to get a Nobel Prize. So one thing that we did was, we teamed up with a few colleagues in our physics department, and we asked them, do you have a real problem that we can bite into, something that you are actually interested to find rather than Kepler equations or something like that? And they came up with a very interesting problem of defocus of cathodes. So they are doing electron microscopy, and apparently there is some defocusing effect. They had a very small number of measurements, so actually 8 measurements for every energy level. So you can see that on this funny graph. And they had a model that was crudely wrong, so it was very, very different. Couldn't really even get closer to fit those points. And they were actually looking for let's say a more generalized or glorified model. And these are very, very talented physicists. They sat for 2 weeks and they came up with something. We said, okay, don't let us know. We will try to figure it out. And indeed, it took us some time as well to get everything in place. But once we improved the algorithm, because there were a few things associated with symmetry breaking that gave us some hard time. But once we figured those things out and improved the algorithm, in a matter of 20 minutes, we would figure that equation that they came up after 2 weeks of effort. So, and that was on a laptop, not on a the largest machine that you can come up with. So I know that a lot of people like to think about Terminator and Doomsday and where we will be in the future. So on the one hand, I don't think that physicists are not necessary, especially here, sitting in the Newton Institute. I should be very careful. The days are not numbered. However, I do think that it can really help them, right? So they don't need to tell anybody that they were using the Nobel Prize machine to come up with a wonderful mathematical model that may help them to get somewhere, right? So I think that's the right attitude that one needs to take here. So most of this work we have done in the underground, to be honest, because now I'm doing quantum computing. It's not really strongly related, as you may assume. We didn't try to discover some quantum effects yet, so that this is really far from that. So there is a very long list of things that we wanted to do that we never got to do, which may be great if any of you would be interested to have a continuation study. I can elaborate on each. Some of them are actually, I think, quite interesting. So now we come up with explicit expressions. So f of x equals to something. Often we have implicit relations, and this is something that is also useful. I mentioned abstract primitives. You may want to incorporate something like, I already trained a network. I believe that that's a great module. That's my object. I don't want to touch it. So this is another interesting thing. Probabilistic formulation, looking into different fidelity measures, complexity measures, differential equations. For some of them we did some work. We patented them, but not all of them, and definitely there's a lot of rigor to go further. Symmetry breaking was really a challenge, because imagine that if you find an equation that x plus y is completely equivalent to y plus x, right? Now, indeed, if you have a global optimizer, you can explore all of those solutions that are exactly equivalent, or you can somehow communicate those equivalences in a sensible way to the algorithm. So there's surely a lot more to be done here, but thanks to that, actually, we managed to significantly reduce the computation time. Stability is another one. We did some interesting work in that perspective. That was, again, talking about stability as a critical aspect. We were challenged with that element ourselves. Dimensionality analysis is another thing that we didn't do. So imagine that if I know what are the units of some of those variables, I can actually be much more effective in figuring out what is the equation. Sensitivity analysis happens by itself, but maybe this is something that's worth some enhancement. We didn't go into systems of equation, which is another interesting extension. We did some work on parallel, but again, the sky's the limit is in terms of what one can do. So to summarize, we introduced here a globally optimal computational discovery framework that is a free functional form and incorporates an unrestricted set of operators. So we have a lot of freedom in what happens, but with freedom comes responsibility. So you need to figure out what interesting problems you want to tackle and how to address them. The approach promotes small data learning. We get relations that we believe are more universal than those that you would get with a data-driven approach, and of course we promote interpretability of those models, which is critical at the times. The use would mainly be an adjunct to scientists that try to promote some scientific discovery, but I'm sure that there are many other usages that we definitely didn't even consider. I listed that long list of things that still need to be done, but hopefully even with some preliminary work, some new interesting insights to our world can be discovered. Thank you very much.
Thank you. Leo, for this great talk. Oh, a lot of questions. Nice. Okay, so let's start over there.
So, Lior, I was wondering if so when in these problems, you have to put in the operators, right? So what happens if you put in, I don't know, the wrong ones or too many of them? Do you have to have a small subset, or if you have so many, does it fail?
That's an excellent question. So we do, when we do those studies, we deliberately put too many of them because otherwise it's cheating. However, we pay a price for that, right? Because computationally, it significantly increases the search space, and you know, you need to be conscious as for, again, if that freedom, there is responsibility, and you need to be conscious. Obviously, if you provide the wrong ones, you would get the simplest expression that uses those in order to represent the underlying function that you have. Hopefully, it's a better proposition than starting with something that you already defined, right? At least you have some freedom between those operator primitives to choose something that is more appropriate than a given specific one, right? But it's definitely a big issue. I wish we would know how to, especially computationally, address that in a very good way. Yeah. Thank you.
Did you try to just put like all the prime numbers in a sequence and see what formula is satisfied? Because that's like the simplest thing. Eventually.
Yeah. So we didn't get to primes. I mentioned
price. It's gonna actually non-double price. Why not? It's gonna help for the quantum computing part as well. Because
now, on quantum, actually, so on quantum, we try to do factorization in a different way, right? We build essentially Shor's algorithm is building an interferometer that counts repetitions and by interference, by constructive interference. But we didn't. I'd be very interested to discuss how this can be done, right?
Yeah, very exciting results. Thanks a lot. So you said in the end that you also have some results on, let's say, partial differential equations to learn those. I mean, can you?
So unfortunately,
So
actually, to be honest, that was the original driver of this work. So we were doing some work with a company, and at some point I got frustrated by the fact that the model was, they had some first principle model that was wrong. Obviously, all models are wrong, George Box, but it was definitely wrong, and we didn't know whether we need to account for thermodynamical effect, whether it was accounting for some more of conservation laws. There was some flow in porous media, whether these are chemical reactions that are interfering. So we didn't know, and the original thought was, if I would be only capable of figuring out those differential equations and discover them, and these are actually it's a limited set of primitives, right? Divergence, rotor, gradient, the adjoint of the rotor if you are not doing this on the discrete level, but it's a quite limited set of operators that you can definitely model, and then you can see what type of permutations or between them can essentially model your problem better. So we did some work specifically trying to figure that out, and later on we had a patent in this framework, but unfortunately I cannot really show results for this. I wish I could. I'm sorry.
Getting back to the differential equations, I mean, you can set up dynamic systems where you cannot really distinguish between coin tossing. So, how on earth is this one going to do that?
So I wish I could say more, but you're absolutely right. You can discover different dynamic equations. Assuming that you have
chaotic dynamics. I mean, I was just going to.
So if you have chaotic dynamics, you will find it's a good question. So I don't know. If you think about the model, you have two different sources of error, right? One is epistemic, and the other one is aleatory. Some of them you can actually explain. The other ones are completely chaotic and independent.
I mean, example from biology, you have, for example, transitions where there's an idea, there's an idea that you can model cell development as phase transitions in the phase space. The transition phase might be a bit almost at the edge of chaos, not purely chaotic, but as elements of edge of chaos. So, and this, in systems biology, you don't have really good first principles to lean on. So this could be an idea, but how would you fish out the ODEs or whatever you want to fish out from that kind of data? I mean, it sounds a bit obvious.
So as long as there is an equation that, that can articulate the relation between what you observe and the variables that you put in, you would find the simplest one. Now, whether that equation is the one that necessarily you're looking for, I don't know, because it's a question of whether you put the right primitives in place and whether within the language you're capable of articulating such a chaotic system. If you are, you should be able to find it. That's the deal, right? But I'll be very happy to discuss it further. This is something that we definitely didn't look into, so it's a very interesting proposition.
Thank you very much for these very nice questions. Let's thank him again.